Okay, this morning I'm going to talk about dinosaurs and their demise. We're going to go to a location out west. Next. Thank you. That is in the state of Wyoming. Next. More specifically, it's southwest of the Black Hills. It's a place of lots of trees. No, not at all. And spend a lot of time looking for trees for shade. This is part of the grasslands of the western United States. I visited that location for the last 4 years in the summers, a total of about 6 weeks of time to look at the rocks in that particular area. The place becomes famous because of the actions of a person by the name of John Bell Hatcher. Hatcher was a field assistant. He was the person who went out and dug dinosaurs for the person whose picture is in the bottom there on the left, Othniel Charles Marsh at Yale University. Beginning in 1889 through 1892 for 4 field seasons, or 3 field seasons by this number, it's 88 through 92, 4 field seasons. He dug out a bunch of dinosaur bones, Triceratops, Edmontosaurus, and thousands of mammal bones that brought this particular location to the attention of the world. From this particular locality, the first Triceratops was in fact excavated, or at least the first Triceratops skull was excavated. Hatcher took out a total of 32 skulls from that particular location over the next 4 years of excavation. There's 3 of them pictured here. Next, in the Smithsonian Institute of Natural History Museum there, the Triceratops that's on exhibit is actually got the head from one location that Hatcher excavated from and the body bones of another specimen that he picked up at that time. You go to the American Museum in New York City, the skull on that mounted exhibit is one of Hatcher's that's not one of Hatcher's skulls. It's another one that was found later. The rest of the skeleton is found in another state, but the two of those are from this locality. The very first T-Rex specimen found, which was a fragment of a jawbone next that you see there at the bottom, was collected in 1900 at this location. Subsequent T-Rexes were found in adjacent states. Next. The first Edmontosaurus specimens were excavated in this particular locality. 2 of the specimens are shown here, collected by John Bell Hatcher. One's in the Smithsonian and one's in the Peabody Museum at Yale University, where Othniel Marsh was. Next. Also, this is a fun little dinosaur. There are a bunch of dinosaurs, but this is another one that people might have known about. Pachycephalosaurus is a dome-headed dinosaur. This beautiful specimen was found near the location where I've been for the last few years. Next. When John Bell Hatcher investigated the rocks in this area, along with the specimens, he described the rocks that the specimens were taken from. Basically, they amount to 2 different rock types. There's mudstone, made from mud, and sandstone, made from sand. And the whole formation is made of those things. Now, on this hillside, as an example, next, the sandstones are sometimes not continuous. If you follow them along, they thin out and disappear in 2 directions. They're a lens of sandstone. Based upon this, Hatcher concluded that the entire formation was basically made of a bunch of mudstone or mud with these lenses of sandstone in the midst of them. So the idea is that this was constructed in what we call braided stream situations. Next, similar to this kind of idea, you're looking at a stream that wanders back and forth, creating sandbars in the stream. Those would be the sandstone lenses. And then every once in a while it floods, and mud will get deposited in what they call the overbank deposits in the surrounding countryside. Next. So imagine a cross-section through this would have some sand and gravel there in a lens across the stream, and then the rest of the area would be covered with mud from the flood deposits. Next. So the entire formation can be summarized as a pile of mudstone with occasional lenses of sandstone in them. And there's a few, every once in a while, what we call stringers of lignite, basically coalified wood in thin layers all the way through every once in a while through the formation. And that amounts to about 99% of the entire formation. The whole thing is about a half a mile thick. And so think of how long it would take for braided streams, to dump a few inches of mud out every spring and accumulate an inch or so of sand during the course of the year. It would take thousands of years, if not millions of years, to in fact produce this particular formation. All along the way, we have buried in the muds and in the sands dinosaurs, tiny little mammals, plants of various types. There are clams, there are garfish, scales in there quite commonly, turtles, alligators, things that would be living in the creeks and the streams, as well as organisms that would be living aside from that. So here's the picture. We have millions of years of accumulation of this material in this particular location, with these critters living happily along for that duration. At the top of the formation, there is you see a double black layer there. There's a double layer of lignite. As you go up the formation, the lignite, these coal layers, get thicker and more extensive. At first, you can only follow them for a few feet, then you can follow them for hundreds of feet, then you can follow them for as long as you want to, and then they begin getting thicker and thicker. In the formation above this, they get up to 300 feet thick. But here, the transition between this formation and the next one above it is denoted arbitrarily by this double layer of lignite at the very top of the formation. Interestingly enough, studies at that location where that transition is made between what's called the Lance Formation beneath it, named after Lance Creek that runs through it, and the Fort Union Formation above it. Looking carefully at the chemistry of this, we find that there is a spike in iridium and other rare earths. These are things that are normally found on the Earth in low quantities, but there's a very high concentration of them right there at that double lignite boundary between the two formations. And that high concentration of iridium and other rare earth elements is thought to be extraterrestrial. Again, it's found on the Earth, but in rare quantities. It's found in greater abundance in an asteroid. So people have pointed to this iridium anomaly, this high amount of iridium at this point, as a point when an asteroid hit the Earth, more particularly hitting the Yucatan Peninsula in Chicxulub crater there in that location. And this is at the top of the formation, the very top of the formation, is identified as a point of asteroid impact. Given that dinosaurs are found throughout the entire formation and not found anywhere above this, it looks as if the asteroid, in fact, knocked the dinosaurs out. And that's the reason that you've probably heard the classic line that dinosaurs lived for 250 million years and then were killed by an asteroid at the end of that time. So there are two interests that one might have in this particular formation. One is the dinosaurs themselves, and two would be that this is the end, apparently, of the dinosaurs. So if you want to know what happened to the dinosaurs, this is a formation you would study as a forensic geologist, paleontologist, to figure out what killed them. You got the bodies, you got the circumstances, let's figure out what killed them. Well, again, according to the conventional wisdom, the asteroid knocked them out. It happens to correspond with the very end of the formation, which is also the last of the dinosaurs. I began studying the location next 4 years ago, visited again each of the summers for the last 4 summers, and spending a total, if you add them all up, of about 6 weeks at the site. I had to ask permission from a lot of ranchers, so I'm going to put that in here now rather than stick it at the end where no one pays any attention to it. I am indebted to the graciousness of many ranchers who allowed me to walk across their land, drive across their land, in order to look at the rocks. They thought I was crazy, of course, so they couldn't understand why I wasn't interested in the dinosaurs, I was interested in the rocks. I'm the forensic paleontologist. I want to know what caused them to die. I'm not interested in them, per se, except as bodies to examine to figure out something about their death. I don't like collecting dinosaurs because I can't even fit one in my car. It would destroy my car if I did. So I'd much rather collect clams. I can collect 1,000 of those and put them in the back of my car with no difficulty. Upon investigating put this back in, the rocks in this particular location, though, I immediately began to realize there are some things that don't quite fit the traditional scenario of a braided stream depositing this over a long period of time. One are next 3-foot-high crossbeds. Now, beneath the person that's standing here trying to show this, illustrate this, there's layering in the sand that indicates the sand was, in fact, humped up into what would actually be sand dunes. Next. So these would have been sand dunes that moved across the screen from the left to the right. The next sand dune would come and cut the top of the previous sand dune off, and then the next sand dune would do the same with the previous one. So we've got water, and it's got to be water because the objects that it's carrying are not just sand, but also things like dinosaur bones and things like that air, wind just can't pick up. So we're talking about water moving fast enough and deep enough to produce dunes that are 6 feet high. If you've got 3-foot crossbeds, that's half the dune cut off. That means the whole dune is 6 feet high. So 6 feet, a 6-foot high sand dune means you've got to have water that's at least 5 times that deep in order to produce that sand structure. So the water's got to be more than 30 feet deep. It's got to be moving at about 1 meter per second at the minimum in order to achieve this, and it's got to do so over a prolonged period of time to move the sand waves, to move the sand dunes along in several different levels. This is not the kind of thing that we would expect in a braided stream situation. We just don't have enough water for a long enough period of time, deep enough, to in fact explain these, and they're very common in the unit. Next. We also find some crossbeds that are not made of sand, but they're actually made of gravel. They're then making up rocks that are called conglomerates or rocks made of other rocks. Their crossbeds in these now require water to be moving much more rapidly to pick up not just sand, but actually gravel, and then stack it into dunes. These are spectacular sedimentary structures, which would require water moving at several meters per second, very deep and very fast, not the sort of thing you'd expect in a braided stream. Next. We also have some interesting critters found in the deposit. Talk about the bodies that we're trying to examine. 2 mummies of dinosaurs were discovered in these sediments. They're both Dinosaurus. They're both found by, not by Hatcher, but by a person who followed him in time. One is located now in the Senckenberg Natural History Museum in Frankfurt, Germany. That's on the lower left. The other one is in the American Museum of Natural History on the right. And both of these, if you look at them, they're sprayed out in a very interesting way for a dinosaur that is bipedal. It's a duck-billed dinosaur. This is not how you would expect a duck-billed dinosaur to die and fall over dead. If he's roadkill on the side of a road, he's not going to be splayed out with his feet like this. They have their feet underneath them normally. To have their feet out like that means they're actually broken in order to be in that position. These are in very strange orientations. They are not the orientation of death you would expect in a braided stream situation. They're apparently picked up by something rather catastrophic, put into a position which basically breaks their bones or distends them into an unusual position. In fact, a position that's very common in whole specimens in the fossil record that we don't quite understand, which involves the neck being curled back almost with the head looking back down their back. We find this in many dinosaur specimens around the world. We don't know why this occurs, but it occurs in no living organism when they die. But it's found in the fossil record rather commonly among the dinosaurs. Something in their burial was quite unusual, not, again, what you'd expect in a braided stream. Plus, this is a mummy. He's preserving the internal organs, the skin, the whole, and it's a big organism. This guy stands up. Well, I wouldn't be able to if he stood on the floor here, I wouldn't be able to reach even his shoulder. He's some 25 feet tall. He's nearly 40 feet long, counting the tail. Even if he laid down and you stomped on him a bit, he'd still be 4 or 5 feet thick. It's really hard to bury a dinosaur that big in a braided stream situation fast enough to preserve all of his internal structure. So this requires, again, a whole lot more water, a worse catastrophe than can be expected in a braided stream situation. Next. We also have things I like better. Clams in the deposit, sometimes in high concentrations. Here's a clam bed. There's a lot of clams in there. See what I mean? I could pick up a set of clams. I can pick up 100 clams in a moment, put them in the back of my truck, car, and I could leave there with that. This is a layer of clams that's about 8 inches thick that I traced over miles of area, square miles of area. That's a lot of clams. And it's not the kind of thing you would expect in a braided stream. How in the world do you collect that many clams and dump them over miles of area? It's not what I'd expect. Next, there are also bone beds of layers of the strata that have a bunch of dinosaur bones in them. Here's an example of one. So a picture I have of a Triceratops bone bed at one location. There's several bones pictured in the picture. The one of greatest interest here is the one next that is circled. There's several bones here that are in the same layer as the sediments, and then there's one bone that's going perpendicular to that sediment. One thing about the bone beds that's really amazing is some of these bone beds are extremely extensive. In one location, there's a friend of mine who's been digging dinosaur bones at one bone bed since 1996. He takes out about 1,000 bones every year. He's been doing that for over 20 years. He's not even begun the process of digging out everything from this particular bone bed. I have traced that particular bone bed over 20 square miles of area. 20 square miles where every square meter, you have 4 or 5 dinosaur bones in that. We estimate there are 15 to 20,000, just one species, Admonosaurus bones in that one bone bed. How do you get that many dinosaurs, that many bones in one location? Again, it's kind of like the clams. It's not something you'd expect in a braided stream deposit. Also, this phenomenon of the vertical bones. For years, the friend of mine who's been digging in this site used to laugh about, and they had jokes about the fact that as they dug down into this unit, the sandstone that they're found in, they'd find no dinosaur bones in the first foot or so. Then they'd start encountering dinosaur bones, and they get more and more abundant and bigger. The first dinosaur bones they get would be toe bones, the tiny little bones of the animal. They're only about this long. One little toe bone, one little finger bone would be about this long. The femurs are this long, okay? You can't pick them up. They're huge. But the first ones, if you work from the top down, would be finger bones. So they used to laugh about the fact the dinosaurs were upside down with their fingers pointing up. But the fact is that as you went down, after a while, I asked him, now wait a minute, let me ask you a question. Don't answer it until I complete the question. Do you find the following? As you dig down, you find nothing for a foot. He said the whole formation's 3 foot, the whole sandstone unit is 3 foot thick. Do you get no bones for 1 foot? Then you get bones for 1 foot, and then you get no bones for the bottom 1/3. And when you're in the midst of the bones, there are small bones at top and small bones in the bottom and big bones in the middle. He says, yes. How did you know that? He said he didn't know that for a couple of years because they'd go down to the bottom of the bones and stop. They didn't bother to go all the way down, but eventually they figured out it was exactly what I described. Well, I said, that's really cool because that is evidence of the fact that this was deposited in a mud flow. We've got a bunch of bones picked up in mud or sand that is moving underwater at probably 200 miles an hour along a surface and then finally stops, freezing in place. As it's moving, the center of the mud flow doesn't move with respect to itself. It's moving at the same speed the mud flow is moving. But the bottom is running along a surface, and there's friction on that surface. So it slows the bottom of the unit down so that any bone there's a velocity profile. If you're near the bottom of this, the part above you isn't moving as fast or is moving faster than the part beneath you. So you tend to rotate and you tend to move into the middle where everything's moving in mass. If this was done in the air, then the bottom of the unit would have no bones in it. All the bones would be moved up towards the top of the unit, and the bones would increase in size as you went up the unit. If it's in air, the thing about air is when the thing's moving through the air, there's very little friction at the top. But if you're underwater, lots of water, the top is also under friction. So the top, if you were on the top, you would get rotated towards the middle. So that if you're underwater, deep underwater, when one of these mud flows, wherever you're at, you're going to be moved and rotated towards the middle. And so the little bones will end up, they don't get rotated as quickly as the larger bones. And so they'll be the last ones to get to the middle. And all along the way, you can have bones in any orientation because they've been rotated into that position. So this means that these were underwater mud flows that covered tens of square miles at least. We think it's much more extensive than that in actuality. This is not something that can be explained by a braided stream deposit. Next. We also find that in places where we find Triceratops in particular, at the location where my friend is digging at one particular bone level, the rancher took me around and showed me 12 other locations where Triceratops had been taken out by previous workers. All 12 of those sites had interesting characteristics. The Triceratops was always found in a layer of plant hash. It's kind of this where the hammer is located there, about halfway, a little over halfway up the picture. There's a chocolate brown colored mudstone that if you take pieces of it and break it apart, you'll see thousands and thousands of little tiny pieces of plants, usually the leaves and some tiny little branches. But in addition to that, you find amber pieces, tiny pieces of amber, sometimes as large as a 1/16 of an inch in diameter, usually not extensive. But the thing is full of all sorts of plants, plant parts flat. When you find the leaves, they are all, each leaf is flat. Little tiny leaves that aren't even folded, and there's this amber. That means that the plants were carried in water, because in water the leaves will stay distended. They will actually flatten out in water if they were plucked while they're still green. So the plant leaves have to be green. That's also evidenced by the amber. The amber is the sap that came from breaking the leaves from their joinings. And so the little pieces of sap indicate that the plants were picked up while they were green, carried in water so that the individual leaves flatten out and get deposited flat for a long distance, long enough for the leaves to distend themselves. And then the Triceratops are in amongst these things. And the Triceratops are kind of funny. Some of them, a couple of those mentioned by John Bell Hatcher, were actually nose down. The skulls, by the way, are about 3.5 feet in diameter. They're about 4 to 5 feet long from the snout to the back of the head, and they're found sometimes nose down in the sediment, which is not what you'd expect them, not the direction you'd expect them to be in. I was at the excavation of one of these sites, and here's a little parenthetical note. Most people that are excavating dinosaurs are interested in the dinosaurs. They care not how they died. They don't care. They ignore the dirt they're in, the sediment they're in, the rocks they're in, because that's a pain in the neck. That's what you got to get rid of to get to the bones. And they don't care about the orientations of the bones. They just get all these things back to the laboratory and stick them together into a nice mount. When you see them in an actual site where the forensics, don't touch the body, is what I say. I want to know how they died, how they got buried, and they ruin all that when they rip the thing and take it out. So these 32 specimens that were taken out by John Bell Hatcher, we have no information on the circumstances of their death and burial. The few examples where I've been able to see an actual excavation have been most amazing. There's one that I saw where the dinosaur, the Triceratops, again, his skull was upside down, his nose faced right into the ground. Underneath him, when they took his skull out, they found his shoulder blade. That's the wrong side of his skull, okay? And then underneath his shoulder blade was a leg, a full leg, all articulated. That's the rear leg, not the front leg, underneath the shoulder. The specimen was mostly there, but it was in pieces. It was like you'd carved up the thing and then laid all the pieces in some random order in place. What? How does that work? I've seen this a number of places. You can see it at the Dinosaur National Monument out there, the Camarasaurus, the big Camarasaurus, long neck dinosaur that's there in the revealed for everyone to see. All the Camarasaurus is there. His head is there, his neck is there, his legs are there, his backbone and all that. But nothing's in the right place. He's got his neck over his leg. He's got his backbone under his head. He's got his. It's just all the pieces are there, but they're in some random order. How's this work? Well, the best way we know to explain this is that the Camarasaurus, or the Triceratops, is floating and bloating. He is rotting as he's floating in water. His skin holds his body together, but as his body begins to break, the leg breaks off and hangs there with the skin. And then another leg breaks off. Oh, I'm grossing you out, sorry. And so you've got this, by the time the specimen gets buried or drops down to the bottom, he's now got various limbs in various orientations, and the heaviest part of a Triceratops is, in fact, the front of his skull. And he'll go face first down, and then his various body parts are still attached by skin and get buried with him. This would actually explain the Triceratops specimens that we find. They're found, so apparently the Triceratops floated and bloated for a long time with plant material. So what this means is we had plants living and Triceratops living, because he's got skin and all that stuff attached in order to explain this. They're picked up by something, they're carried in water a very long ways, long enough for the plants to distend and for the Triceratops to rot, and then deposited as together. So we're talking about being carried in water a very long ways for a long time, probably weeks at least. This is, again, not something you can explain with a braided stream deposit. Next, in my travels over the area, I don't know, I never actually logged how many miles. It's a couple hundred miles I walked through the plains of Wyoming, looking in gullies, looking for rocks, and documenting what I found in my notebook. As a result of all of these studies, I realized that the rocks the pile of rocks that you find at any given location, so along that red line, which is about 6 miles in length, at several locations, I've got enough rocks stacked to get up above that point that I can create what's called a stratigraphic column, a representation of what rocks are found there. The white would represent the shale rocks, or the mudstone rocks. The yellow would represent the sandstone rocks. And it turns out over the 6 miles that you can, in fact, trace the sandstone units across the entire length. They're not lenses, as was claimed by John Bell Hatcher. They are, in fact, these are each at least 30 feet thick, some of them 100 feet thick. So they're between a 30 and 100 feet thick, foot-thick sandstone units that are found across 6 miles that way. And going north and south, you can trace them over 10 miles to the north and south. So over a 60 square mile area, I can trace individual sandstone units and mudstone units over the entire formation. So we've got sandstone beds that are 30 to 60 feet thick. That's much too big for braided streams. You can't get sandstone that thick continuously over large areas. Got to have some place for the mud. So either that or this is an enormous braided stream, a stream that's the size of a continent. That's the only way you could explain it. Or we're talking about not lenses of sandstone at all, but in fact sheet sandstones. They're found over huge areas, and sheet sandstones are not found in braided streams. They're only found in oceanic deposits. We can only do that in a huge body of water. Rather, it's a submarine, it's an underwater sandstone, which suggests that this entire area was covered by ocean. By the way, its current elevation is between 4,000 and 5,000 feet above sea level. So back to this observation of those lenses, it turns out this is the wrong scale. Those sandstone lenses there are in a single mudstone unit that can be traced across miles in all directions. Those are individual little sandstone units in one mudstone unit. So the scale is much bigger than anyone had ever imagined here. John Bell Hatcher is looking too closely at it. He didn't see the pattern that's there because the pattern is bigger than he or anyone else was used to observing. Another observation in the area is convoluted bedding. This is something the formation is actually well known for, famous for. On the other hand, I've dug through the literature and I've found no reference to it in the literature, even though everybody that's familiar with the formation knows about the convoluted bedding. No one has published on it. So when I published on it, the Geological Society of America meeting, for example, last fall, that's the first time anyone had ever made that claim or talked about it in the scientific literature. Convoluted bedding would be sandstone units where they're not cross beds or flat beds, but in fact the sand goes every which way. Convolutions in sandstone we know come from, and I've had a chapel previous to this talking about these, come from earthquakes. The sand was originally deposited with normal layering, flat or cross beds, and then it's full of water at the time that it was formed, because it was formed underwater. And then somewhere after that, the area was jiggled with an earthquake that causes the sand grains to close pack, forcing the water out, and the water escaping causes a modification of the lines in the sandstone and causes these convolutions. So basically, these convolutions require that the sandstone has to be deposited very rapidly underwater, and then before it gets dewatered, it's been sitting there too long to lose its water, it's got to be hit by a big earthquake. And it's got to be a big earthquake because these puppies are really big. Some of these are up to 30 feet high. The smallest ones that I ever paid attention to are about 3 feet. The largest ones we see on the present Earth, with the biggest earthquakes we've observed in the last 3,000 years, are less than 1 foot. The smallest ones I'm seeing here are in excess of 3 feet in thickness and up to 30 feet. They indicate earthquakes hit this sandstone soon after deposition underwater of enormous power. These are earthquakes that actually the secular literature, when they observe them elsewhere in the world, they say they are unearthly earthquakes. There is no conceivable way that they can be formed by any earthly process. They involve so much energy. So they've invoked asteroids hitting the Earth to explain the energy that's required to produce a 3-foot thick seismite. I've got 30-foot thick seismites. This would require something much bigger than asteroids. In fact, if you hit the Earth with a big enough asteroid to explain a 30-foot seismite, you would destroy the Earth. You would destroy life on it. There would be nothing left. So these are bigger than asteroid impacts. Enormous earthquakes. They're found not just once through the unit, but over 2,500 feet of these. I've got 60 to 80 of them. So every 50 feet or so, I've got a seismite. I've got a big earthquake impacting these sediments. This indicates that we've got, again, this sand that's being deposited up to 100 feet thick is being deposited underwater very rapidly, then being hit by enormous earthquakes, much bigger than anything that can be explained even by asteroids. And all this while little dinosaurs are getting buried in it. So moving to another question next. I'll put all this stuff together here in a moment. We look at the landforms, the shape of the land. And they've got some funny landforms here. Next, I got to explain a few things for you to understand what I'm about to say. What water can do. When water is moving really, really fast over a surface, it has the ability to erode into that surface in a planar fashion. If there's enough water moving fast enough, it just shaves the stuff down and cuts straight down, not creating a channel. It just creates a flat surface. It just erodes down that surface. If you slow the water down, it starts channeling. But if you got enough water moving fast enough, it erodes what we call peneplains, or flat surfaces, flat erosion surfaces. So looking back at our picture next of the United States, we've got the location there out west. You see at the bottom of the screen a rough profile of North America. You start at the west coast, you're at sea level. East coast is the other side on the right. You're at sea level at the bottom of the slide. As you go away from the coast, of course, it comes up out. The land rises up out of the sea. We hit mountains from each coast. Shorter, tiny little mountains in the Appalachians, a mile or less than a mile. And then in the Rockies, they rise up much, much higher. Average lower height is more than twice the height of the Appalachians, and usually the peaks are 3 times the height of the Appalachians. And then coming back down on the other side, of course, we end up with the Great Plains. If you take a a ride in a car, like I did coming from the Appalachians, driving out to Wyoming, I drive downhill to the Mississippi River, all the way to the Mississippi, and then drive uphill all the way out to Wyoming. There's this broad V shape in North America, Central North America, on either side of the mountains. What causes that? If, in fact, you look at the rocks, you find that the layering of the rocks is cut by this. So whatever rocks are there have been cut into this V shape in North America. So the evidence is that at one time there was water over the entire area east of the Rockies. At one point, it was the area that I'm speaking of in Wyoming was underwater. The Appalachians were completely underwater. Next. And then water moved away or down. Water is running off of North America. And as it does so, next, it eventually reveals the Appalachian Mountains, and that diverts the water, which was originally going completely to the east. There's then water moving between the Appalachians and the Rockies to get around the Appalachians to go out to the ocean, and that is eventually what erodes next the large. Back one. That erodes then this V-shaped pattern. So think of the mountains on either side of North America as the banks of a river. And the river is lying between them and moving south. Those are the retreating waters from a time when the entire continent was covered with water. Next, so water, when it's moving very, very fast, is able to peneplane, cut erosion surfaces. If you slow it down, it begins dropping the material that it has picked up in eroding, and it lays it down in sheets. That sheet deposition, which follows the peneplane situation, we then drop the sediment and create what's called a pediment on top of the peneplane. If we look back next at our site in Wyoming, on the hilltops, so there's the creeks and the rivers and all that sort of thing where I could generally find the rocks. On the tops of the hilltops, I find these boulders, gravel and boulders. So the boulders can be up to 1.5 feet in diameter or so. It's easy to identify where they come from. No, they're not sandstone, they're not mudstones, so they didn't come from this area. In fact, they didn't come from anywhere within 10 miles of this area. I showed the background picture for one purpose. Way off there in the distance, barely visible underneath the phrase Black Hills, are the Black Hills. About 50 miles away, we have a hilly area that actually is the source of these rocks. These rocks can be located, their original source is from those Black Hills way over there. How did they get here to this location? So next, in that scenario, so here we are, Black Hills are to the right of the star there, mostly in South Dakota, across the border from the area that I was studying. So if we look next at this situation of water leaving the area, it at first is going to be higher than the Black Hills and going to be moving off to the west next. Then the Black Hills are going to, as the water goes down, the Black Hills are going to rise up out of the water. The water is going to run around the Black Hills to get again out to the west, leaving the area next of the Black Hills being high with a peneplane in between. Again, a river valley between if you wish, between the Black Hills and the Rockies. With the water having moved to the south, it creates this V-shaped valley in between the two. Then there must have been some sort of, after the water has disappeared, there's apparently some sort of rain, lots of rain, that was actually able to erode the Black Hills and next take cobbles and boulders from the Black Hill and spread them out over that surface between the Black Hills and the site where I was working. Next, then erosion following that took out a lot of the area between the Black Hills and my site, leaving those boulders just on the tops of the hills, a long ways away, 50 miles away from the Black Hills themselves. Next, continuing the story, as you lower the energy of water, again, at the highest energy, water erodes in flat surfaces. Lower the energy, it begins depositing in flat sheets. Lower the energy even more, it tends to channel and cut canyons. At first, it cuts very wide canyons with steep sides, and then as it decreases in power, it will drop sediment in there and fill those canyons, half fill those canyons, and then less water would create another canyon inside that canyon, and you can have canyons inside canyons inside canyons as water decreases in strength and intensity. Next. That's what we see in the location I was studying. Let's see, picture off to the right shows a person standing on top of rocks, but between him and the rocks, there is this layer of what's called colluvium. It's basically a mud, it's an unconsolidated mud. And in places, it's only a couple feet thick, like there, but down on in other locations, it's 20, 30, it's even places where it's 40 feet thick. So this colluvium is sitting on top of all these other rocks. Where is it found? What's the pattern? The pattern is that it's found very thick in the river valleys, and it's found of zero thickness at the tops of the hills where the boulders are, and it's increasing amounts as you move towards the valleys. So there's evidence that there was a large river running through this area, denoted by the blue there, taking a topo line and just running it across there. We have evidence of very large rivers. These are a mile-wide river, the size of the Mississippi, running through this area that's now nearly a desert. Inside that river valley, which was cut and then deposited half filled with debris, is the current creeks and rivers. It's the little white line that's in the midst there. Oh, next slide shows a close-up of one part of it. You can see the white. That's the current Lance Creek running back and forth across this valley of a huge previous river. There was an enormous river that drained this area that left a flat valley behind, and the current Lance Creek is wandering back and forth across that surface. It's hard to see in the next picture, but you see those little dark green dots in towards the horizon? That's showing you where the current Lance Creek is. Lance Creek, it runs along those dots back and forth, but it's actually flowing away from us down the valley, wandering back and forth. The valley actually goes from the far left to the far right. The hills you see about 2/3 of the way to the right are the one side of the valley, the right side of the valley, and the ones all the way to the left are the other side of the valley. So it's a very wide, 1 mile wide valley with Lance Creek running around through it. This indicates that there was once a very large river that cut the valley, deposited half filled or most filled that valley, and then the little river or creek now runs through the middle of that. Next, let's pull it all together. So let's look first of all at the Lance Formation itself, the formation with the dinosaurs, trying to think what is going on here, what happened. We have evidence of billions of trees, enough to create 300 feet of coal. So billions of trees, tens of thousands of Admonosaurus, innumerable other plants and animals are overtaken by water while still alive. Number two, those plants and animals are carried and floated for a very long time, probably weeks at least in time. We've got evidence not just of the rotting of the Triceratops, but there's evidence that dinosaurs ran over the top of bones of other dinosaurs, scavenging for food in this same period of time. So it's a long period of time that organisms are floating and bloating. Number three, mud, sand, and those organisms are rapidly laid down in layers tens of feet in thickness over an area that now covers several western states, not just eastern states. They're big states in area, at a location thousands of feet above sea level, about a mile above sea level, by if you wish, a moving ocean over that particular area, a mile above present sea level. And then also at the same time, we've got continent-shaking, life-destroying earthquakes, bigger than anything caused by asteroid impacts, are occurring on a regular basis while all this is occurring. All this you raise sea level a mile to explain these rocks, you've covered the world with water. And each one of these earthquakes is capable of killing every organism on the planet that's standing on land. So we've got apparently a water catastrophe that floods the entire world and kills all the organisms in the world. I don't know any other way to explain this than by, next, a global flood. Following that, next, we have that flood water is receding from the continent. We have evidence at this particular location that the waters left this particular area and created in the process an erosion in the center of North America that creates the peneplain between the Appalachians and the Rockies. So this is a scale of looking at the continent of North America as a river, as the waters from this global flood receded from North America. Following that, then there was catastrophic rainfall rates, enough to supply rivers in what is now a near desert. Rivers the size of the Mississippi, cutting first of all, eroding rocks, boulders off of Black Hills and surrounding the area with a sheet sediment of boulders. And then as the rainfall decreased, it cut channels that produced rivers the size of the Mississippi way out there. Can you imagine what they were producing in the center of the United States when they all come together? Then as waterfall decreased, eventually we get to the situation we have today, where we have the tiny little creeks and rivers are running back and forth through these underfit valleys from that time. So this indicates that we have both evidence next in this area of the global flood, next having killed the dinosaurs, but also we have evidence of those floodwaters receding, and then a period of time after the flood where we have high rainfall rates that decrease down to the present, all consistent with what Scripture tells us about the history of the earth. Next, the Lance Formation evidences events in the past. You can look at it one way, which is the way that John Bell Hatcher looked at it, and the way that almost everyone looks at it today, and conclude that the earth is old. These things occurred over millions of years. You conclude that death has been happening this way for millions of years. It's the norm for the universe. You conclude that dinosaurs lived and ruled on this planet long before humans ever came along. You can conclude that our present understanding of braided streams helps us understand what happened in the past in the Lance Formation. And you can conclude that the dinosaurs died because of bad luck. They got hit by an asteroid. And you also conclude from this the Bible is wrong. Or you can look at the very same rocks and look at them in a completely different way, namely what the information the Bible would give to you, and realize that a better way to explain it, because it can explain it better than the other scenario, is that the earth is actually young. Death is due to man's sin. It didn't come in, it wasn't there before humans sinned. Man actually ruled over all animals, including the dinosaurs, and God intervenes in history in a global flood when he got mad with humans, and dinosaurs died in that judgment on human sin. All these are claims that the Bible makes. The Bible is true. It's been true all along. Speak to the earth, Job says, and it shall tell thee. It shall speak of God and those things that he has done. There's evidence here in the rocks of the earth that the dinosaurs died in that judgment that God brought upon man because of man's sin. That same Bible says that judgment is coming in the future as well. And Jesus is the only ark through that judgment. Do you know him? It's imperative that you do.